both cases, this was equal to v1 squared plus v2 squared plus plus vn squared.
So when you say vector space, is it safe to assume that it's always going to be considered a matrix, or can it just be like a set?
Well, the vectors themselves are just these objects.
Okay.
So, I mean, they have a matrix representation. Okay. That was for real vector spaces, and then for vector spaces over the complex numbers, if we wrote, let's write W here. If W is the column vector, W1, W2 down to Wn, then W transpose, we have to conjugate when we take the transpose. If I forgot to put the star in, we need to put the star in. And so this is W1 star, W2 star, up to Wn star. Okay, so I think I might have forgotten to put the star in when I wrote it last time. So go ahead and put that in your notes. Yeah, question?
I guess why must it be conjugated if that's within the scope of this explanation?
Yeah, because remember we want
because we want it to be positive.
this thing has to be greater than or equal to 0.
Yeah.
So if we want the same thing for the magnitude of this vector W squared, then we can write it again in dot notation. You know, you have to just, this is, you know, you can put a little C on that dot for complex.
Okay.
But this is equal to W star transpose W in matrix notation. And this is then, will be the magnitude of W1 squared plus the magnitude of W2 squared. Okay, so that's the big difference, and we're working in quantum mechanics, we're going to be working in vector spaces over C, so we always have to do this. Whenever we transpose our vectors, we just have to conjugate them to make sure that this inner product is positive, or positive with itself, or a vector dotted into itself. Okay, so there's a notation for that. So dagger dagger. This is identical to the conjugate transpose. Okay, so we can write, so W star transpose is the same thing as W dagger. That's the notation that's just commonly used. Okay, any questions so far? All right, so now I'm just going to show you the notation in we're going to cover this again in detail, but there's a notation called Dirac notation. For vectors. Okay, and if I write a vector W, this thing is written like this, okay? And this is called ket. All right. And so this would be like column vector. And then this W dagger is written the other way. This is called bra. Okay, so these two things make what's called a bracket when you put them together. And so when I take the inner product here, if I write the inner product, W dagger W, this goes to the following. And this is called a bracket. Okay, so that's the Dirac notation. And we're gonna see a lot of this, and the reason that we write it like this is because it's very convenient. This notation is actually very nice and powerful. So, and you'll see the power of this notation when we start using it. Here, it's just kind of superfluous because we already know what we mean by this, but it's a very, very powerful notation. Okay, so that's going to be the difference between, that's the difference between a ket vector, that's a ket vector, this is a bra vector. Okay, and they live in different vector spaces. Right, I cannot add, they're vectors, I cannot add these things to each other. They live in different spaces. Okay, so I can take an inner product, which is written like this.
Sorry, one more time. I think I just missed that. What can you not put together?
So illegal, something illegal would be something like this. This makes no sense.
Okay.
That's because they have different dimensions, right? They were like a matrix. One is a big column, one is a row.
They live in different spaces. They just don't belong together in any way. They have the same dimension, but they live in different spaces. Okay, so this makes no sense. Okay. So let's do it just a very quick example here. So this is an example that's in the notes. So if compute the magnitude squared of P for P equals P1 E1 hat plus P2 E2 hat with P1 equals 2 plus I and P2 equals 3 minus 2I. Okay, so that means these are complex vectors now. This is a complex vector. So that means if I want to take, if I want to take the magnitude of P squared, I have to use this notation. So I have to use P with the complex dot product there, which means I have to do P conjugate transpose times P in matrix notation. So this thing then would be the following. So P1 is 2 plus I and P2 is 3 minus 2I. But when I transpose it, I have to take the conjugate, so I'll have 2 minus I in the first position here, and then I'll have 3 plus 2I in the second position. Okay, and so now when I do the matrix, I take this row and then I multiply it by on the column. I'll have 2 minus I times 2 plus I plus 3 plus 2I times 3 minus 2I. Okay. So now this will just be what, 4, this is 4 plus 1 plus, this will be 9 plus 4. Is that right?
I think the difference is.
Yeah, so, okay, so this is 18. Okay. So this is what I mean about conjugating. When you do this, make sure that you remember to conjugate your row vector. Oh, I think this is your pen from yesterday.
Oh, probably.
With this
Thank you.
notation for dot product, is it required that one vector be a transpose of the other?
No, we can, no, for example, if,
Like if you had 2 row vectors, would you still be able to dot them?
yeah, sure, I mean, these are, P is, if P is equal to P1, let's just make, so P is, P1, P2, and Q is equal to, Q1, Q2, then, P, the complex, dot inner product here would be P1 star, P2 star, Q1, Q2, and so this would then be P1 star, Q1 plus P2 star, Q2. Okay? All right, are there any other questions on the inner product and this notation?
Not yet.
Okay, so when you start solving the problems, you know, just keep all of this in mind, except, you know, we'll be writing things now, we'll be writing things like, you know, W, we might write something like P is equal to P1 phi 1 plus P2 phi 2, okay, where these are like the, phi 1 and phi 2 are like the basis vectors.
It looks like in this example that you did take the transpose of P and you also followed that you have to conjugate them as well. So what you're saying is that you could not just multiply P1, Q1, P2, Q2 and add them?
Correct.
Okay, yeah, that's what my question was.
All right, any other questions? Yeah.
This is a minor one. So like that phi 1 in the, I guess in that one that's the ket, would that, if you wrote that in matrix notation, if you wrote that in normal notation, it would just be phi hat or something?
Yeah, I mean, this could be the vector, this could be the column vector 1, 0, and this could be the column vector
Okay,
0, 1.
just want to make sure.
Yeah, just like, yeah, exactly. Yeah, so this could be, you know.
So I don't know if I missed this, with the example where you have the P squared equals the P dot P, is that little C under the dot there?
Means we're doing the complex inner product.
Complex inner product, got it.
Also, it does not matter which one you convert to a transpose, right?
It does.
Oh, it does? You have to convert the first one to the product.
It will, yeah, it will make a difference. Okay, and we'll get to that. While we're here, let's just, it does matter for the following reason, because if let's just continue with this example. So P, if we take P dot conjugate Q, that's this expression. This is P1 star Q1 plus P2 star Q2. Right, I can write this. Imagine just pulling out the star, or I can conjugate the whole thing. I can write this as P1 Q1 star plus P2 Q2 star, and then conjugate the whole thing. I can write it that way if I want. But what is this? This is, in parentheses here, this is Q with this complex conjugate dotted into P star. Okay, so when I switch the order of P and Q, I will get the conjugate. So
Okay.
that's an important point with this notation. So in Dirac notation, this means that P, Q, the inner product here, is equal to Q, P conjugate. Okay.
So unlike normal real dot products, they're not, I think commutative is if you can swap them, but it's, well, because they're not the same, they're not equal to each other.
The same object, so you can't really call it commutation.
Yeah.
But, yeah. I mean, we're actually, this is a different,
Operation.
it's a different operation in a sense, but it has, in physics, this actually has a physical interpretation, which we'll talk about. Okay, everybody comfortable? Any other questions? Okay, so once you work through a few problems, I mean, it will become more evident. So, all right, so let's talk about switching basis sets. So this is section 2.4 in the primer. Okay, so for example, suppose we have two bases, E1, E2, up to En, and E1 prime, E2 prime, up to En prime. Okay, and I'm gonna, just for convenience, I'm gonna drop the hats on these things just because it's just a lot of writing. So the same vector V. So we can write V in terms of the first basis, or we can write the same V in terms of the second basis. We can just write it in terms of the second basis, but with different coefficients that we have the primed coefficients. Okay, and so so we can write then V1 E1 plus V2 E2 plus ... is equal to V1 prime E1 prime plus V2 prime E2 prime plus ... And now let's go ahead and assume that both bases are orthonormal. So we have EI dotted with EJ is delta IJ, and then E prime L dotted with E prime M is delta LM. Okay, so that just means that, you know, I have little basis vectors and they all form just a nice rectangular array in dimensions. Okay, so we have this equation, and now we can, what I want to try to do, what we're after as we go through this process, is trying to calculate let's calculate the V, the unprimed V's in terms of the primed V's, okay? And so we can do that by, for example, dotting through, let's dot this expression, we'll dot in from the left side, the E sub I, okay? So dot E sub I from the left, and that will give us, so when E sub I, when I take the dot product with this sum of vectors, it will pick out, you know, it will be 0 for everything except when the other E is the same as I. So that will pick out the V sub I. So that will give us V sub I on the left, and then on the right, we'll have V1 prime. And now there's no reason that the prime basis set and the unprimed basis set have any particular relationship. So here we have a bunch of E1 dotted with E1 prime, and then we'll have plus V2, E1 dotted with V2 prime, E1 dotted with E2 prime, plus dot dot dot, plus Vn prime, and then, oops, sorry, EI, I was doing EI. EI. EI dotted with En prime. Okay? So, now, I here runs from 1 to n. Okay, so I have n equations here. So that means I've got V1 is equal to V1 prime, and now I'm just, this is E1 dot E1 prime plus V2 prime E1 dot E2 prime plus dot dot dot, and then V2 is V1 prime E2 dotted with E1 prime plus V2 prime V3 would be V1, V3 dotted with E1 prime. Okay, so you get the picture here down to V sub n, which would be V1 prime V sub n dotted with E1 prime, and so on down to Vn prime, En dotted with En prime. Okay, so we have n equations, and then there's n terms over here on the right-hand side. So we can write it as a matrix. So then we can write V1, V2 down to Vn is equal to this big matrix of all of the dot products of the basis vectors, and that's going to act on V1 prime, V2 prime, and so on. So this matrix is just E1 dotted with E1 prime in the top corner, it's En dotted with E1 prime in the lower right corner. This is E1 dotted with En prime, and this is En dotted with E1 prime. Okay, so we can write this matrix then, we can write, that V is equal to this, matrix R here, if we call this thing R, times V prime. Sorry, I forgot to close my column vector there. Okay, so what we're gonna do, we're gonna switch bases frequently because it's convenient, and so we'll be trying to find things that, now if this is just, you know, we can think of just a simple two-dimensional example where we have E1 and E2 here, and then E1 prime and E2 prime with some rotation angle theta, then this is just a rotation matrix. Okay? And so it's easy to go back and forth between these two. I can take, if I were to do this the other way around, I can multiply both sides of this by R inverse. So I can write that V prime is equal to R inverse on V, right? If I wanted to if I wanted to switch bases the other way. And for rotation matrices, they satisfy R transpose R is equal to the identity matrix, or R transpose is equal to R inverse. Okay, so this is also just R transpose V. All right, so let's do a quick example in 2 dimensions of this.
Can I get a picture of the board before you go second?
Oh, sure. So let's do a quick example in 2 dimensions. So let's let E1 and E2 equal X hat and Y hat. And we'll let E1 prime, E2 prime equal X hat plus Y hat over the square root of 2, and X hat minus Y hat over the square root of 2. Okay, so this is just a 45-degree rotation. And if you calculate R by taking the inner product, the rotation matrix you'll get will be 1 over the square root of 2 here, and then you'll have a minus sign down in the corner. Okay, this is just rotation by 45 degrees. And yeah, okay. All right, and then let's also just cover one tiny bit of notation before we get started on some real physics. Well, I'll save that for a little bit later. Okay, so are there any questions? Kind of wrap wraps up our discussion of the linear algebra review. Okay, so let's go ahead and start off talking about some physics. So, the birth of quantum mechanics was a really interesting story, and it was a fascinating story about how things happen in science also, because it was people went kind of kicking and screaming into quantum mechanics. They didn't want to believe some of the experiments that people were doing were really bizarre, and even Einstein had a lot of trouble with quantum mechanics. I mean, he didn't have trouble understanding it. He had trouble with what it implied about the physical world. He really didn't like it from an interpretation standpoint. But anyway, so as far as the chronological kind of, some of the people in chronological history here is interesting. So people of importance, Max Planck is probably one of the first. He lived from 1856 to 1947, and Planck was the person to essentially solve the ultraviolet catastrophe problem, by sort of by fiat, by saying energy is quantized, and so that's where he comes in, and this was done in it was 1900 was when his paper came out, and so it was nice. I think it was 1900, 1901, something like that, and so that's sort of a nice start to the notion of wind and quantum ideas start making their way into their science vernacular. And then there is Werner Heisenberg. And he lived from 1901 to 1976. And he introduced matrix mechanics. And the uncertainty principle. So he had, he did other amazing things, by the way. When he did this, he came up, you should read about his matrix mechanics. It's really bizarre because mathematicians already knew about matrices. And he went to some island in, I forget, it was like some vacation island that people in northern Germany go to, like, what's the sea up there? Right north of Germany.
Isn't that like?
North Ocean?
I think it's like by Denmark, like the Denmark Strait.
It's a sea or something.
It's not like the Arctic Sea, is it?
No. It's,
And we barely know American.
Well, it's called.
Why do you think we're here?
Think about it.
I do believe that pretty much everything like really far south is called the Southern Ocean, and everything really far north is called the Northern Ocean.
okay, well, I forget where. So anyway, he was like, he had bad allergies, I guess, so he went to this island, and he came up with matrix mechanics. And
Is it directly north of Germany? Or?
It must be.
yeah, I mean, I think so. It's like north of I know Rostock is in like northern Germany, and I think it was either, I can't remember if he lived there or he had family there.
Is it northern Atlantic?
No, it's a sea. I can't remember the Baltic.
Yeah, it's Baltic.
Oh, right. The Baltic Sea.
Just north of Germany, and to the west is the North Sea, and then to the east is Baltic. So it's got
So it must have been the
both.
North Sea then? Whatever's north of like Rostock. Anyway, okay.
So north of Rostock is Baltic.
Okay. Well. So he came up with these two things, and they were really instrumental in and the ideas. I mean, the matrix mechanics, this was, non-commutation of observables.
You did it on vacation, you said?
Yeah.
Which is why we should have more vacations.
Exactly.
What does that mean?
I was about to ask the same thing.
This? Okay, we'll come to that.
Okay.
But that was, it's a big idea, and he came up with other, I'll mention later, some other ideas he came up with, but the uncertainty principle, this is,
What is the word at the very end? Non-commutation of
observables.
observables.
Yeah, we'll define it, what an observable is in a little bit shortly here. Observables are essentially just things you can measure.
Right, there are properties that are defined by real numbers, right? Not like the whole imaginary stuff going on.
Right, that's, yeah, right. They have to be real. Okay, so that Werner Heisenberg was a big, this was early on, this was in the, I can't remember exactly when matrix mechanics came out, but this was before, this was pre-1920, say. And then we have Max Born. So Max Born was, Max Born came up with what the modern interpretation is. Okay, so he was the one who came up with this idea of what is the state function. And then we have Erwin Schrödinger. So Erwin Schrödinger is, he is the co-inventor. So Werner Heisenberg is the co-inventor. So it was basically Heisenberg and Schrödinger. So, and he came up with the Schrödinger equation. Which was a wave equation, which was very different than this matrix mechanics. Okay. And then, yes.
So Heisenberg was working on the uncertainty principle and he was like 18, 19, pre-1920. He was born 1901.
Yeah,
He's a hot shot.
All right.
Jeez.
Yeah, he was a hot shot.
Making us look bad.
Okay, yeah. No kidding. I was failing like intermediate algebra when I was.
Well, but then he was a Nazi. Well, then he worked for the Nazis and when he was 40. So.
Everybody.
Yeah.
IBM, Volkswagen, Coca-Cola.
Okay.
All right, so let's cap this off. There's a lot of people here I could put down.
Well,
next.
maybe, I'm not sure how college was then, I don't think they had to go get PhDs until they were 29 yet.
Yeah, Paul.
I mean, I think it varied just like it does here. It's just like it does now. It's just that, I mean, Heisenberg really was one of those just absolutely original thinkers. So, okay, and then there was Paul Dirac. So, Paul Dirac is not, Paul Dirac is probably, he's for certain one of the greatest scientists who ever lived and one of the greatest physicists from the 20th century. Dirac he held the chair at Cambridge that was Newton's chair. So he was a professor of, mathematics at Cambridge. And Dirac he's outlandishly, brilliant. And he sort of came along and he looked at all the stuff and then he wrote his book in like 1920 that sort of just was, like okay, this is what quantum mechanics is. And that's how we're learning it today. So this is, you know, he clarified.
Another teenager.
He clarified and set notation for everyone. Okay, so Paul Dirac is, if you want to think of him, he's sort of like Leonid Euler or something, you know. Like calculus was just kind of a mess, everybody had different notation, and, you know, Newton was fighting with Leibniz and all of that, and then Euler came along and just, you know, had this beautiful notation that was, you know, you couldn't argue with, and everybody uses it to this day. So Paul Dirac did the same thing for quantum mechanics, and it's Dirac's notation that we'll be using most of the course, because it's so beautiful. Okay, so that's just an overview of everything. And so quantum mechanics was really kind of finished. I mean, non-relativistic quantum mechanics, which is what we're studying in the course, was finished basically by around 1920. And after that, you know, a lot of the tests of quantum theory, people were trying to examine quantum theory, make sure it was correct by studying things like emission spectra, so a lot of atomic physics, emission spectra, absorption spectra, those kinds of things, where you had a really fine test of quantum theory. And of course it passed flying colors. It's, you know, quantum theory has never been, there's never been an experiment that's been in contradiction with quantum mechanics. So it is, you know.
What year was the double slit experiment?
It's supposed to be young experiment, right? Wasn't that like 1800s?
No, I thought that was like in the 60s.
I think, I mean, that was, so the double slit experiment for light was pre-quantum mechanics.
Right, it was done at Canada, right, in like
Oh.
1860 something.
I'm
Yeah.
thinking of Rutherford.
The electron, actually.
If, for electrons, I don't think they did it for electrons for a while, because they couldn't really, it wasn't easy to.
The other had to be after Broy, right? The Broy.
Right, I mean, well, yeah. De Broglie De Broglie's work was in, if it was between the 10s and the 20s, or right after in the 20s or something like that. Had to be pretty early, yeah. But the interpretation, of course, and all of the quantum mechanical aspects of those things weren't known until later. Okay, so let's start examining some of the experiments. The most important experiment is what's called the Stern-Gerlach experiment. This was the experiment that really
It's what's on the cover of the book.
yeah, it is, yeah. Okay, so let's see what they did actually. They had an oven. And then you have a pool of silver. Okay, and this is an opening, and you have silver atoms coming up. Okay. Now, silver. Do we still have a? Yeah. Okay. So silver's atomic number, you can see back there, is 47. So there's 47 protons in the nucleus, and there's 47 electrons to balance the charge. And so 46 of these electrons paired. And now, I'm not sure exactly how much of this they understood at the time of this experiment. So this was 1922.
So this is an olive, so was it a liquid state? This has cool, I think, from here?
Yeah, so it's just really hot, and then you have, silver vapor up here, and then you have a hole in the oven so they can come out. And in between, here we have poles. The faces of the poles here are they're shaped so that the field is non-uniform. So you have a strong B field here, and then it gets weaker as it goes up. So this is a non-uniform B field. Okay, so these silver atoms go streaming through. They go through this magnetic field, and then you have a screen over here that collects. When the silver atoms hit the screen, then you have an image here. Okay. That's the experimental setup. So now let's. At the time, people were, again, people were not sure what to make of quantum mechanics, and so they were doing this experiment to test, in particular, if classical physics was going to answer this question, or if it would require a different answer. And so classically, what do we expect? For the image.
Wouldn't it be like kind of a Gaussian, like it would be most in the middle and then it would diffuse across the image?
Yeah, that's pretty much right. But since we know that electrons have a magnetic moment, let's go ahead and see if we can reason our way through that, but you're right. So we have to take into account the angular momentum. L, which is just R cross P. So we want to consider the angular momentum for an electron. And we're assuming now, because 46 of these other electrons are paired, this is an even number. There's, if the electrons are little bar magnets, then, they cancel, these 46 cancel each other out. So there's one electron here that's basically making the measurement what it is. Okay, so let's just recall a simplified model. Okay, an electron's charged also, so we can't completely ignore the charge on the electron. But if we have, let's say there's some surface area A, and we have a charge Q, and the period, let's see, is of a radius R here, with the period T. So if we assume that we just have a charge going around in a little circle, we know that the magnetic moment mu remember from classical mechanics, this is the current times it's the current that's in the loop times the area of the loop divided by C. That's just from classical physics. So let's see, what do we have? We have L, the angular momentum here will just be the mass times the velocity times r for a circular orbit. And the velocity here, if we know the period t, that's just 2 pi r, the circumference divided by the period. That'll give us the velocity. And then we have a is equal to just pi r squared. So we want to write mu in terms of, we want to write, what we're trying to find is mu in terms of L. Okay, so, okay, got it. Okay, so now, if you just, area here is pi r squared, and then I can solve, I want MVR in the numerator up here so that I can write this proportional to mu. You can do that with the variables here, it's just a little bit of algebra. So you get Q over 2 MC times L, the angular momentum. Okay, and these are vector quantities, so we should write it like this actually. So the magnetic moment should be proportional to the angular momentum. Okay. All right, now, so if these things are streaming out of the oven, if I've got, we have these mu's are pointing in all sorts of different directions coming in. Right? They should be randomly oriented because it's just a hot mess in there. And so what else do we have here? We know that the potential energy of a magnetic moment in a B field is it's minus mu dot B. Okay, so here we'll assume so B of Z is in the Z direction, but it's not a constant field. It varies. So it varies with position. Okay, and so the force is minus the gradient of the potential. So this would be then plus mu dotted with d by dz of B. So this is mu I'll have a force here that's dependent on the strength of the field. So I will separate I'll have a force that is dependent on the gradient of the field. So that's mu z bz. Okay. So again, the mu has many components here. Mu will be mu x hat plus mu y hat plus mu z hat.
Would would that be the force of only the z component then?
Yes.
Okay.
Well, I mean, yeah, because it's only, because B is only varies in the Z direction.
Right, okay.
So it depends on the gradient and mu sub Z. But mu sub Z should vary, you know, if this is isotropic, I expect mu Z to just vary all over the place, right? So we expect the image to be as, I mean, it should be just a uniform block here, basically. Because every orientation should be there equally. So you should just have a uniform distribution.
But they didn't get that.
No. That's why everybody freaked out when they did the experiment.
Why is there a reason why it's drawn as like a rectangle here? Is that something?
No, you could draw it, I mean, it would really depend on, I'm just.
Are you saying it would fill the whole screen?
Well, I mean, let's just, you know, yeah, it could, I mean, it just depends on how you set your.
If I remember
How long you leave it running.
I thought it would be more like a circle that's a little bit denser in the middle maybe, or?
Yeah, I mean, the important point here is that it's uniform from top to bottom. And you can shave off the edges here if you want, or, you know, but it's uniform from top to bottom.
Okay.
And is that what we're getting from the mu sub z?
Yes.
Okay.
So it goes, you know, and that's, if you have these atoms bouncing around all over, you know, in this vapor, and they're hitting the walls and doing everything else and streaming out, you have these mu's in all sorts of different directions, we expect a uniform just distribution there. So the measured distribution just looks like this. It's just two lines.
So
Okay.
what would have been the result, I guess in both cases, if there hadn't have been that magnetic those magnetic bars there? Would it have been like?
It would have just been uniform.
It would have just been uniform as well. Okay.
Well, I mean, you know, if you put a little collimator here, you know, something like this, you would just get a, you know, you would just get a spot right in the middle.
Well, I was saying if those magnets weren't there, if there was no magnetic field.
Yeah, if there was no magnetic field, then that's exactly what you would get. These things would just go right and hit the screen.
Oh, okay.
So I'm guessing there was only two possible magnetic moments?
That's what this tells us. Yeah. Yes.
So for the expected image, you wrote uniform distribution there, so it's not like a Gaussian where it's right in the middle, and it fades out. It's solidly uniform.
Yeah, because that's what I said in the beginning. So I got
yeah.
Well, I mean, you would expect, on the surface of a sphere, if you just project the z component of everything on the sphere, you just get a uniform distribution.
Okay.
So, yeah, it's because mu z is taking on every value.
Okay.
Yeah, that makes sense.
It's taking on every possible value equally, there's no most probable value.
Okay.
Right.
That makes
Okay.
sense.
Well, I mean, yeah, I mean, it's just a uniform distribution.
Okay. Gotcha.
Okay, so,
Distribution in statistics usually makes me think that there is a most probable value.
no, uniform just means there's nothing most probable. I mean, uniform means that anything is equally likely.
Oh, okay. So that it was like if you graphed the distribution, it would just be a line.
Yes,
Okay.
yeah, exactly,
It wouldn't be a curve, it would be a line.
correct. Yeah, okay, so this was a huge, huge deal. We just got 2 lines. So this means has 2 states for the magnetic moment. All right, and so this is called,
The spin?
it's called the spin. This is, when they did this experiment, because you get physical separation, they call this space quantization. Okay, so that's what they called it. Nobody uses this terminology anymore, really, but what it does imply is that you have 2 states for the magnetic moment, and so that's, this is the spin. Up, so you can call it up, or you can call it down. You can call it plus, or you can call it minus. You can use arrows. I can call it spin up or spin down with arrows.
And does it really have like any sort of, like there's no way to define whether it's like clockwise, counterclockwise, it's just something that's opposite to the other one?
Yes, it's just, 2 states. You can call them anything you want.
Wasn't Pauli who originally called it like 2-value electron thing or something?
I don't know. I don't know if you did.
So, like, I guess based on what the electron spin is, I guess determines which line it would end up at?
Yes.
Okay, but now you're getting into some really deep stuff. That's
They
a
didn't
really-
know this yet.
That's a really deep question.
Okay.
Now which particles follow this rule? Because I know it's not, there's other particles besides electrons that follow this.
Sure, I mean, any particle that has spin can be in principle separated into its components. So if you take a spin 1 particle, you'll actually have 3 components. Things like that, okay? Nuclei themselves have different spins, and nuclear magnetic resonance, which is a really, that's the basis of MRIs and that kind of thing. MRIs are really very simple, but in science, magnetic resonance is used for nuclei that have, some nuclei have crazy spins, like 5 halves, 7 halves, 9 halves, and things like that, and have a whole bunch of states. And so, you can determine the structure of a molecule, for example, by just doing magnetic resonance measurements on them.
Yeah, that's right. For electrons, it's positive 1/2 and minus 1/2 usually they say, right?
Yes, yeah. That's what we're going to, we're on our way there.
So we'll explain why it's a 1/2.
Yeah, we're going to, for 2-state systems, then it's very convenient to denote them as spin 1/2. I mean, we're gonna call it, this is called a spin 1/2 system. Okay, but to your point earlier, it is a deep principle in quantum mechanics that you don't know. I don't know, so I can't just say this is a collection of spin up and spin down electrons here. And I knew that before they went through the magnetic field.
Right, because the magnetic field would reorient them, right?
Well, classically, it reorients, right? Quantum mechanically, it's a measurement of the spin. Okay, so you don't know what the spin was until it hits the up or down line. That's the measurement. Okay, okay? So we don't know until it makes the measurement.
Yeah,
So
for all
does
we,
the
for all we
spin relate
know,
to the spin relates to the energy, which also has an uncertainty.
I'm sorry, say that again?
Does the spin relate to the potential energy, which would give it the uncertainty?
It would have, well, I mean, certainly, I mean, the energy is only relevant, the energy of the electron spin is only relevant like sort of when it's in the magnetic field classically. But, yeah, let's just kind of put that thought on hold for a little bit, because we'll come back to when we start talking about energy, like what's relevant. Right? I mean, right now the electrons go through here and we don't know their state until they hit the board here, the image board. That's when we know whether it's a spin up or a spin down. Okay, so, yeah, let me just, so the measurement idea in quantum mechanics is a really deep one, because it's so
philosophical.
I mean, you can get very philosophical talking about it. It's not easy to figure out what's actually happening inside the magnet here. You can't ask the question really, and it's the same question as what slit does the electron go through?
I see.
If you look, you destroy the interference pattern because you figured it out beforehand, right? But you're making another measurement there, right? So if you have the electron going through the two-slit experiment and you shoot light photons at it to see which slit it goes through, then you disturb that electron, you'll localize it somewhere, and then so you'll have made a measurement on that electron, and that will destroy the interference pattern. So
The philosophical question would be, what is a measurement, or what counts as a measurement?
right, it's a really good question. Go ahead. Yeah.
So would it be correct to say that the spin of the electron is just undefined before we measure it, and it just has a certain probability of being up or down?
Yeah, it is. Let me write it down for you. So let's call this, okay, let's use kets here. Let's do a plus ket and let's do a minus ket for up and down. Okay, so after the state of an electron, before it gets to the magnet. I'll just write now psi is a state vector. Now it's just going to be an equal mixture. It's going to be an equal mixture of up and an equal mixture of down. So that's the state of the electron, okay? So in this, when we write this means that I haven't made a measurement on this state yet. This is a superposition of spin up and spin down. Okay, so that's, what does this mean? This means that in some sense, in a very real sense, these electrons are in this state, which is,
Or at least 46 of them are, right?
no, 46 of them are paired. So you can think of the first 46 are like this. And then the 47th atom or electron is in this state.
But does it seem like we would know that they have to be in pairs yet if we didn't know that they could only be in two states?
Well, yeah, I mean, we have to, I wanted to give you the actual experiment instead of just shooting electrons, so, because this is the way they really did it.
So if we're working with 1/2, why is the coefficient in front of the kets 1 over square root 2? Or did you just like decide that number?
No, it's a good question. So, what we're going to see is that we want, well, okay, so let's go ahead and, we can go ahead and do this now. We would say then that we have, a basis state. Our basis is this, it's plus and minus, these are two ket vectors. Okay? And I can write my state psi is a linear combination, so C1 plus C2 minus, that's just a state with two vectors. Now, what we want, okay, I'm gonna write it now, psi. This is the inner product of psi with itself. All right, so for a physical state, we want this thing to equal 1.
Okay, so then,
So it's a normalization.
yeah, gotcha.
So let's go ahead and write it out. So psi, now so this is a ket vector, but if I turn it into a bra, this is how I do it. I write C1 star conjugate, remember, plus C2 star minus. And those are that's how I write the bra vector. So then we can take the inner product. So if I take the inner product, then I will have C1 star plus C2 star minus C1 plus C2 minus. Okay. And now I'm going to use the fact that plus is 1, minus is 1, and then plus minus is equal to 0, and minus plus is equal to 0. This is just orthonormality of our vectors. And then we can write that, so psi inner product with itself will be, this plus is going to hit this plus here and give me a 1. I won't get a contribution from these two because a plus will hit a minus and I'll have this case. And then this one will only give me a contribution from this minus here will only give me a contribution from that minus.
Okay.
So we'll end up with magnitude of C1 squared plus the magnitude of C2 squared.
Okay, that makes sense.
Okay, and this has to be 1. And so if we want the,
Why is it?
if we want them, if we have an equal probability, then this has to be a half and a half. So 1/2 plus 1/2 equals 1, so C1 is 1 over root 2, and C2 is 1 over root 2.
That was a lot for me.
Don't worry, I didn't plan on covering all this tonight, so I'll do it again, we'll do this again in detail next time.
Oh, it's 47.